எங்க போயிட்டு அதெல்லாம் கேட்பாங்களா கேள்வி செய்வாங்களா இல்லை நீங்க கேட்டு போறீங்களா அவங்க ஆன்லைன்ல இருக்காங்களான்னு தெரியல check the audio it's going there or not that will be just a second so we will go to the
Hello. Can participants on Zoom hear us?
Yes, I can hear.
Yeah, okay. Thanks, BC.
Yes, Pratik, we can hear. Hi, Adam. Good morning or good afternoon.
Hi.
Zoom participants का volume.
Our speaker la potu vidunga.
So,
Can you speak once again? We are just trying to see if we are able to hear you all. Yes.
Yes, testing. 1, 2, 3.
Yeah. We can all hear you now perfectly. Thanks.
I'm me.
Oh, yeah. Okay.
We'll give it just 2 more minutes because I have 8:58. Are there a few more people coming? I think so. So Adam, we have like an hour set aside for your talk. So something like 50 minutes of talking, 10 minutes of questions. Does that sound good?
Yeah, I think I might run a little bit shorter than that. Originally, I had said that I would only be available for 45 minutes, but then I managed to find someone else to pick up my kids from school. So I can stay for the full hour, but I think my slides won't run quite that long, but we'll see, because I actually also haven't given them a very careful run of time. So.
Great. If you get close to 50 minutes, I'll give you a warning. If you end early, that's great. We can have more discussion.
Sure. Yeah. Can you all see my slides okay?
Yeah, we can see them. Let's just wait. We'll wait 1 minute. Manjari just went out, I think, to grab Gopu. But the slides look good. We've had a lot of interesting discussions already, actually, about VLBI, and it's important for, pulsar timing arrays.
Okay, excellent.
Yeah, but so we're looking forward to this talk. Time, but I don't want to start without Manjari coming back.
Yeah.
So we'll give it a minute. Great. So where is Manjari? Okay. Yeah, maybe we should get started. So our first speaker today is Adam Deller. Thanks for joining us remotely and rearranging your schedule so you can be with us for the hour. And he's going to tell us about turbocharging precision pulsar timing science with VLBI. So take it away, Adam.
Okay, thanks. And thanks also to the organisers for inviting me to give this overview of a passion of mine, the VLBI astrometry of pulsars. It's what I started doing in my PhD about 15, oh dear, more than 15 years ago now, and have been doing ever since. So what I want to talk about today is just a bit of an overview of VLBI without going too deeply into the technical details, but enough to sort of set the scene so you can understand the power and the limitations that it can bring to observing pulsars. And so, yeah, specifically to talk about the frequency range and the regime that we would normally observe pulsars with VLBI. A bit of time on how astrometry works with VLBI, because that's really the most common use case of applying VLBI to pulsar science. And then, having gone through that background, talk about what we can do to leverage more out of pulsar timing data sets by adding VLBI to them. So the principles and some of the recent science highlights sort of broadly grouped into what you can do for an individual source, and then maybe what you can do for ensemble science or pulsar timing arrays more specifically. And then just thinking a little bit, closing out at the end with future applications for pulsar VLBI astrometry. So what is very long baseline interferometry for those who aren't familiar with it? Well, it's basically just regular radio interferometry taken to the extreme. So rather than baselines, separations between the antennas of maybe kilometers, which might be typical for most radio interferometers, we're going out to say thousands of kilometers. And what that brings us, we can see immediately from the fundamental principles of interferometry that the angular resolution will be very, very high. So at a frequency of 1.4 gigahertz or a wavelength of 21 centimeters, if you take an array with a maximum baseline, a maximum separation between the antennas of 8,000 kilometers, it'll have an angular resolution just given by the diffraction limit of about 7 milliarc seconds. So as a consequence of that, VLBI images where you've got a pixel scale of, a milliarc second or maybe a bit less, depending on the frequency that you're using, you can either study small scale structure in the images very, very accurately, or measure positions of sources very, very accurately. Those are the two primary use cases. So I wanted to just briefly mention the names of a few major centimeter VLBI instruments, because I might refer to them later in the talk. The one that I've used most extensively through my career is the Very Long Baseline Array in the USA. And the reason why it's been the one that I've used the most is because it's the only full-time, low centimeter VLBI instrument in the world. So it's 10 antennas, each of diameter 25 meters. So it's moderately sensitive, but not incredibly so. It has a very wide frequency range covering from 327 megahertz up to 86 gigahertz. For pulsar science, we tend to be focused on the kind of 1 to 2 gigahertz range. And it has a maximum baseline of 8,000 kilometers. So by virtue of operating 24/7, it gives the opportunity to both study large samples of sources, because you can get more time than on a lot of the other facilities I'll talk about in a second, but also to observe when you need to, because as I'll come to in a little bit, when we're doing astrometric work, there's generally specific times of the year that we might want to observe. And lastly, I would say that it's also possible to add the Green Bank telescope and the phased VLA, sadly not Arecibo anymore, to the 10 dishes of the VLBA to form what's called the high sensitivity array. And that has much less observing time available, but through the addition of those big dishes gives you more sensitivity. There's also in the north the European VLBI network. And so that's an ad hoc array of dishes, which is the case for most of the other arrays we'll talk about. There's of order 25 or 30 stations, depending on how you count them and which frequency range you're interested in. And they range in size from 10 meter diameters up to 100 meters, covering a similar frequency range to the VLBA, not quite up as high, and a similar maximum baseline, but it's not operating 24/7. It operates a few sessions per year for a few weeks at a time, plus some shorter turnaround sessions. And that's because each of these radio telescopes is not solely doing VLBI. They do their own other observing, including pulsar timing for some of them, for a lot of the year, and only come together to act as a VLBI instrument for some part of the year. Going down south, we've got the Long Baseline Array in Australia. It's a smaller facility again and less time. Again, it's only usually operating about maybe 4 weeks a year, 3 or 4 weeks a year, and a more restricted frequency range. But it has the advantage of location. It's the only Southern Hemisphere VLBI instrument that's available. So for pulsars for many of which are in the galactic plane and hence better observed from the south, it does have an inbuilt advantage. And then the last one that I wanted to talk about was the East Asian VLBI network, which is really a collaboration of 3 separate networks. You've got the Korean VLBI network, the Japanese VLBI network, which is VIRA, the VLBI exploration of radio astrometry, plus some other Japanese antennas, and the Chinese VLBI network, notably now, or sort of at the moment, it's beginning to include the FAST telescope for a very large sensitivity boost. And when those 3 arrays come together and operate collaboratively, that's the East Asian VLBI network. And I wanted to make mention as well that I know that there's been some efforts over the last, more than a decade actually, to commission VLBI observing from the GMRT, and that's another very substantial sensitive collecting area that would be can be advantageously added to a number of these different arrays when that's available. So from a VLBI viewpoint, pulsars, what's important about them? What can we do with them? So I think, as everyone probably knows, they have typically quite a steep radio spectrum, which means that although we might like to go to higher frequency because we'll get even better angular resolution, that's often not possible because the sources simply get too faint. So we're generally pushed to observe at the L band, kind of 1.4 gigahertz for the majority of pulsars. Some of the brightest pulsars we can push up a little bit further, but this is kind of like the workhorse frequency range. The other thing about pulsars that's noteworthy is that they're intrinsically point-like. The size of the emission region, as viewed from the Earth, is of order nano arc seconds in size. So we're never actually resolving the emitting region of the source. However, the multipath propagation that many of you are probably familiar with as manifesting as a scattering tail in the time domain also manifests in the plane of the sky as an angular broadening, and that's illustrated down the bottom left of this slide, where the observer at the telescope sees incoming scattered radiation coming from a range of angles on the sky rather than just directly from the pulsar. And so that leads to an angular broadening. And that's then illustrated in that bottom right-hand plot there, where as you go to longer baselines, which correspond to higher angular resolution, the flux density of the source starts to drop away as it's becoming resolved out by the interferometer. So this can be interesting. You can constrain the scattering geometry by combining the measurements of the angular broadening with measurements of the temporal broadening, because if you assume that it's being dominated by a single thin screen, that can tell you how far along the line of sight that thin screen is. And you can use that to understand and correct for some ISM effects a little bit better than you could without that information. Things of interest might be extreme scattering events, perhaps, and actually imaging the structure of scattering screens as well. But I think that's really a bit more of a niche area. And so in general, we like to, if we can, focus on less scattered pulsars because that's simply easier. But unfortunately, if the interesting pulsar you want is somewhat angularly broadened due to scattering, then you have to live with it, and either you have to observe it at the lower frequency and accept that it's going to be spread out on the sky and hence harder to see, or go up to higher frequency where the scattering effects are lower, but the pulsar flux density is dropping and you need more sensitivity. But so if we're not really, in most cases, interested in imaging the source structure, what's the point of this very high angular resolution? What's the point of getting billions of tiny pixels on the sky? It's all about location, 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 as any good real estate agent will tell you. And so that means astrometry, measuring positions either in 2 dimensions, so that's just reading off from images, where is the pulsar at a point in time, and ideally converting a time series of such positions into a knowledge of the pulsar position in the 3rd dimension. So how far away is it along the line of sight? And I'll get into how we do that in a second. But first, I just want to talk a little bit about the realities of making highly precise astrometric measurements of pulsars with VLBI. And here, calibration is really the key thing. And at low frequency, it's the ionosphere is the main thing that we need to calibrate out. So just to visualize how this works, essentially the relative arrival time of a signal from a celestial source between a pair of antennas encodes the position of the source in one dimension in this simple example on the sky. And of course, in a real interferometer, we have many pairs of antennas, and we observe for a long time, and we get many constraints that way in order to nail down the position more precisely. But we can illustrate all of this just with a simple 2-element interferometer. So in this sort of contrived example here, I've set it up so that the plane wave arriving from a distant source will arrive at these two antennas in phase. And if the source was at a different position on the sky, then we would see the signal arriving with a delay between one antenna and another. And I'm sweeping a few things under the rug here. We don't measure delays directly with our interferometer. We measure phases, and by virtue of having a wide bandwidth and measuring phases as a function of frequency, we can essentially convert back into effectively delay measurements. But I don't think we need to worry about that here. We can just visualize this as saying the telescope, the interferometer, is measuring delays, and from those delays we can infer positions on the sky. Unfortunately, there are other sources of delays that the signal will show between pairs of antennas that are not related purely to geometry, not related purely to where the source is on the sky. So any propagation error that leads to a delay between the expected arrival time and the actual arrival time of the signal from a given location on the sky will shift the apparent position of the source. And so just to visualize that here, I have the same example with the source back at its original position, but the path length through the ionosphere is a little bit thicker over the top antenna than over the bottom, and the signal propagates a little bit more slowly through the ionosphere than it does in a vacuum. And so that means that the signal ultimately arrives with a bit of a delay at the top antenna relative to the bottom. But we don't know that if that's not in our model, and we would then propagate back outwards and say, I think my source is coming from over here, and it's actually not. That position shift is a result of our imperfect calibration. But if we don't know that, if we don't know that there's been a calibration error that's taken place, then we will simply measure the wrong position, and that will lead to much embarrassment later on. So what can we do about that? There are lots and lots and lots of things that affect that can lead to a relative propagation delay, as I mentioned before. A few of them are mentioned down the bottom there. But the thing that typically dominates is either the troposphere at higher frequency or the ionosphere at lower frequency. And because we're almost always observing below 8 gigahertz when we're looking at pulsars, it's really the ionosphere that's enemy number one. So we can try and make our best possible models of the ionosphere so that we take away any propagation delays due to the ionosphere before we start trying to make our images of the sky. But models can only take you so far. It turns out that it's quite difficult to model the ionosphere because it's quite dynamic. It changes on timescales of minutes, tens to minutes. And so what we do instead is use an astrophysical calibrator source. So basically that's a source that's close on the sky to the target source, whose position we know, or at least whose position we think we know. And when we look at that calibrator source, which is shown in blue here, we'll see a relative arrival time delay between pairs of antennas, even though there should not be after we've put in our best model. And so we'll look at that residual error and say, well, whatever that error is, it must be coming from the ionosphere. And so I'm going to correct it so that my calibrator source appears at the right position on the sky. And then I'll take those same corrections and I'll apply them to my target data. And hopefully that means that the target source is now going to be appearing very close to where it should be. It won't be perfectly so, as you can sort of, as is illustrated here, that there's always a bit of a direction dependence to these propagation delays. But if the calibrator source is close on the sky to the target, then the difference in the error will be very small. And so that can greatly reduce the target residual. And through doing that, we can get to the very high precision that I'll show in a minute. So what does doing VLBO astrometry then mean in practice? Really what it means is very, very carefully calibrating your data. So doing the absolute best you can to model all of these propagation delays. Then once you've done that, you make an image of your pulsar, which is going to be incredibly boring. It's normally going to just look like a point-like source. And from that image, you can extract a position. And you do that for every one of your observations over a period of months or years. And then once you have that time series of positions, you can go and fit for the astrometric terms that lead to changes in those positions. So fit for a reference position, a proper motion, so a linear change with time of the position, and an annual geometric parallax, which is caused by the motion of the Earth around the Sun and related to the distance of the source. And maybe for a binary, there might be orbital reflex motion that you need to model and take out as well. So I've just got a bit of an illustration of this from a paper of mine from a couple of years ago with just a very boring example image, relatively low signal to noise, actually, just because if the signal to noise is very high, it's very hard to even see the error bars on the position, the measured position, which are shown in the middle here. So we're basically fitting the centroid of the emission of the source. That gives us a position and an uncertainty. That would give us one of the points shown over here on the right. And then by observing, in this example, 8 times, I think, 9 times, we can then go and fit for those 5 astrometric parameters that I mentioned before. What's being plotted here are the residuals after subtracting off the best fit reference position and the best fit proper motion, just really to highlight the parallax, because that's often the thing that we're most interested in. And then what's shown in the grayscale is a bunch of fits to bootstrap trial fits to what the parallax might be. And from that, we can infer, as shown down the bottom right, what the parallax is of the source, and from that, what its distance is, which is what we are really caring about in this instance. Okay, so that's kind of the fundamentals. If anyone's got any questions, I should say, feel free to jump in, at this stage, because I'm happy to take questions throughout. I can't see if anyone's raising hands on Zoom, so please just sing out if you have a question.
Yeah.
So was that
Adam?
Oh,
yeah. Adam, just a small clarification on that. So the ionosphere is the devil, as you stated. So if you have a large sensitive antenna and rather remotely located antennas in your large baseline array, is there a calibration technique involving subsets of arrays to look at different patches of the ionosphere and improve the astrometric precision?
Yeah, so I have a couple of backup slides at the end. I could jump down to, no, I won't. I'll just describe it. So what the technique that I described here is simple phase referencing, where you measure the ionospheric delays effectively along a single path line per antenna, and then you assume that the delays are exactly the same along that path line to the calibrator as along that path line to the target source. And so the closer you bring the calibrator to the target source, the better that will work. And that's not really dependent on large versus small antennas or anything like that. But there's always going to be a residual error. You can make it smaller by having a closer calibrator, but in general, if you have to pick a closer calibrator, it will be fainter, and pretty soon you'll run out of signal to noise. You won't be able to derive a good solution anymore. But so something that's been worked on quite a lot over the last couple of years is, rather than doing what I would call a zeroth order interpolation, where you basically take the exact same calibration solution that you derive for the calibrator and apply it unmodified to the target, trying to do interpolation. So either in one dimension, where you try and find 2 calibrator sources that are fairly collinear with the target on the sky, and then you look at the differential calibration term between a primary calibrator and the secondary one, and interpolate that differential term to the location of the target. Or more generally, if you have 3 or more calibrator sources, you can try and fit a plane of the calibration solutions in the sky, and again interpolate now in 2 dimensions to the exact location of the source. And so, yeah, in that way, you can try and take the spatial dependence of the ionosphere into account better than just saying, I'll get something as close as possible on the sky and hope, cross my fingers and hope that it's the same in the direction of the target as it was of that one source. Does that answer your question?
Yes. What I was interested is there any quantification of the improvement in the error bars, not just of the direct astrometric precision, but when you propagate it to the parallax distance. In other words, can you actually go order of magnitude better in the parallaxes by using a technique like this?
Yes, that is the. There are claims that is true. So what has been done previously, so the approaches that have been taken are always dependent on the capabilities of the instrument that you're using, right? So typically, the field of view that we have with these VLBI instruments is about half a degree or smaller, because with a 25-meter dish at 1.4 gigahertz, that's a beam width of half a degree. And generally, either we're looking at that frequency or higher, and that antenna size or larger. So the field of view is only ever that or smaller. And the ability to see 3 or more calibrator sources that are sufficiently bright to derive good calibration solutions within that field of view is quite small. Like it would be very rare to see 3 calibrator sources all at once within 15 arc minutes of the pulsar. So what people have done instead is that they slew around. They look at a calibrator, and then another calibrator, and then another calibrator, and then the target, and then calibrator, target. And so that has 2 drawbacks. One, you're losing a lot of time on the actual source because you're spending all of your time looking at the calibrators. And 2, you're not getting the solutions simultaneously. They're quasi-simultaneous, and then you're doing a bit of interpolation in time as well as in space. But that said, people have done that and have shown improvements of up to an order of magnitude compared to kind of what I would call best practice, getting the closest calibrator that you can. But they haven't yet shown that at 1.4 gigahertz. So what would be really, really ideal is to have a nice sensitive VLBI array that has a slightly bigger field of view, like even about a degree would be fantastic. If you had about the same sensitivity as what people currently have, or a bit more, because then you would get 3 or 4 or 5 calibrator sources all visible at once. And so that's something that's likely to be possible with the next generation VLA, assuming that it continues on with its current specifications. But until we have, it may also be possible when using the square kilometer array for VLBI, because whilst the square kilometer array is an interferometer, and we would be phasing it up to use it as a VLBI element, it's one of the requirements for it is that it has multiple phased array beams available for VLBI at once. So you could be looking at a target and several calibrators all at the same time. So I think with those next generation facilities, yes, I think we should be able to get up to twiddle an order of magnitude improvement on what's the best available or the best possible results at the moment. And I'll come to that in a bit more detail later in the talk. I kind of stole most of my thunder from the end of the talk just now.
Oh, sorry. No,
it's okay.
I just mentioned it because the multi-sub-array or the multiple phased array thing which you talked about is already there in GMRT. And one of the things which we were trying was exactly to do the same thing. So split the array into 2 or more sub-arrays and put them on different calibrators. So that takes care of your first limitation of additional time on calibration. So I think it would be very interesting to discuss some of those things at a later point of time. But anyway, you answered my question, so thanks. And sorry for interrupting.
No, that's quite all right. And I'll just round it off by saying, one of the challenges with doing VLBI is that it tends to we make use of whatever antennas we have available, and that means that it's not a homogeneous sample. So you have small dishes, big dishes, phased arrays, etc. And so in a sense, you're often restricted to the lowest common denominator in terms of either frequency coverage or field of view or whatever. And so, like, for instance, if we were to try and do this technique with the long baseline array and add in GMRT as an extra element to the LBA for that, you know, strip of sky that's visible to all of the antennas, we would be stuck with having to work within the field of view limitations of Parkes, which is a 64-meter dish, which is, you know, relatively small, at least until hopefully the phased array feed comes up on Parkes. So there's always like this kind of optimization of what you would like to do versus what you can do with the antennas that are available. Okay, so context shifting back to here. So now back to the application side, having talked about all of the, you know, problems and challenges and whatever. Once you overcome them, what can you do? So there's two main things I think you can do with single sources that are being timed and use VLBI to help them. The first one is directly improving the timing model. So basically removing covariances in the timing model. And the second one is making use of information from VLBI when you're fitting other things with the output of the timing model. And so I'll go through these two in turn. So the first one is, removing covariances in the timing model. And so basically the things we get from VLBI are the proper motion and the parallax, really, and to a lesser degree, the reference position, although we'll talk a little bit later about how that's a bit more challenging. But so if it's possible to measure the proper motion of the parallax to much higher precision and accuracy with VLBI than it is with pulsar timing, then you can go and fix it in the timing model, and then anything else that was covariant with one of those two parameters will no longer potentially end up with the wrong value. And so the most common use case here is the covariance between dispersion measure variations and parallax. And so this is an example from the IPTA data release 2 paper, where you can see this kind of like quasi annual variations in the dispersion measure change, this one particular pulsar. And so if they're not modeled perfectly, and it's quite hard to model them well, that can bleed in to the parallax signature, and you could end up with the wrong parallax when you're fitting the timing data. But if you go and fix the parallax, then you'll actually be able to model the dispersion measure variations better, and that will also mean less power bleeding into anything else that's covariant with dispersion measure change. And I just said all of that. Apart from the fact that it's particularly a challenge for pulsars that are at low ecliptic latitudes, where the pulsar goes behind a greatly varying density of the solar wind at different times of the year. And so this was just another example from a recent paper that I was a co-author on, led by Gao et al., where we looked at this for PSR J2222 minus 0137, and you can sort of you don't need to focus in on the details here, but when you fix the parallax and you fix the proper motion, you see significant changes in some of the other fitted parameters because of that. So the other thing is then, once you've done all that or not, you've got some results from the pulsar timing, and you might need to know something that you can measure better with VLBI to do some kind of additional test. And the prime example here, I think, is doing GR tests using the orbital period derivative of the pulsar. So this is an example from Michael Kramer's paper from just over a year ago now. So the orbital period decay due to gravitational wave emission leads to advance of periastron that's plotted here on the left, and you can model that. You can model what you would expect based on GR and see that it matches perfectly. That's people have been doing that for a long time and only making it look better and better. But the thing is, the observed quantities, what we see, that the orbital period derivative effectively doesn't solely trace GR. It's not only due to gravitational wave emission. There are other contributions from some distance-dependent effects that have nothing to do with the system itself. And so I'll just show what they are here. The first and usually the most important one is what's called the Shklovsky effect. And this is an apparent acceleration away from the observer due to the transverse motion of the pulsar. So it's sort of shown here. pulsars moving across the plane of the sky, but relative to a fixed distance from the observer, it looks like it's accelerating away from us. And so that will lead to an apparent orbital period derivative. And the second thing is an actual acceleration in the gravitational potential of the Milky Way. So the Earth's accelerating, our observational platform, and the pulsar. And so the difference between those two accelerations will also show up in the observed orbital period derivative. So you've got to model those effects and take them away to leave the intrinsic orbital period derivative due to gravitational wave emission if you want to go and test GR. And so the double pulsar 0737 minus 3039 was a fantastic system and is a fantastic system for doing this. It's very precisely measured, the orbital period derivative as shown at the top here. And we did some VLBA astrometry there to provide the distance to the source. And so I'm just showing here the effect of the parallax on the right ascension of the pulsar as a function of time with that same bootstrap plot that I was showing earlier. And then from that, we can get a distance. We actually combined the fitted value from pulsar timing with the fitted value from VLBI. It was a slightly, I would say, perhaps suboptimal way of doing it, but it grew out of the long heritage of data reduction for this project. Anyway, we got a joint distance from that. And from that distance, we can calculate the Shklovsky term, which depends on distance and transverse velocity. And we could calculate the Milky Way acceleration. So those are those two terms here. And then we get a total correction value, which can be subtracted off from the observed PB dot to give a PB dot due to gravitational wave emission. And you can use that then to go and test GR. So this is like kind of the beautiful plot from the paper here, showing all of the post-Keplerian parameters that have been measured by pulsar timing, and then zooming in to the middle here. So every pair of, every parameter gives you a pair of masses for the two pulsars in the system. And if your theory of gravity is correct, then these lines will all intersect at a point, or at least be consistent with intersecting at a point. I'll just zoom in a little bit further here. So the most precisely measured things are the advanced periastron and the Shapiro delay S parameter. And so those two things cross here. And so then the next most precisely measured thing is what sets the strength of your test of GR. And the next most precisely measured thing is the orbital period derivative. So getting that right is really important. So just ignore the dashed line for omega dot there. That's neglecting an effect that shouldn't be neglected, and it was just there for illustrative purposes. So we expect our PB dot line here to cross this point here where omega dot is crossing the S parameter. And so if you go back here, the correction that we made to PB dot was roughly twice the uncertainty of the measured PB dot. So if that correction hadn't have been made, this magenta bar here would not be intersecting with the intersection of S and omega dot, and we would be saying, oh my God, GR is wrong. So it's important to take these things into account, I guess is what I'm saying. And going forward, the precision on the PB dot measurement should improve quickly because the measurement precision adds up very fast as the cumulative effects of the gravitational wave emission pile on. And so whilst at the moment, the precision to which we can make that correction for the Shklovsky effect and for the relative acceleration in the Milky Way potential is subdominant, within a couple of years, hopefully, I forget if it's 4 or 5, something like that, we should be at the point where they're really getting to be quite comparable again. And then we would actually need to improve our distance further if we want to stop that from being the limitation of the GR test. So that's what you can do with a double neutron star system. You can also do other tests for other alternative theories of gravity, in particular, using pulsar white dwarf binaries where the two compact objects have different binding energies. And so this is some results from a paper that was accepted last year and I guess has a publication date of this year from my former student, Hao Ding. So in that work, we looked at 18 millisecond pulsars with VLBI and got parallaxes for 15 of them. And 2 of them, the ones that are underlined here, are ones that are very useful for doing this kind of test for the time variation of the gravitational constant G, or the coupling, the dipolar gravitational wave emission strength that you would get in some of these alternate theories of gravity. And at the end of the day, combining, the results from 4 pulsars together, including the 2 that we refine in this work, we see that, the gravitational constant G is still constant, and, there's a consistency with 0 dipolar gravitational wave emission. So GR is still a valid theory of gravity at this point, which surprised no one, but, you've got to keep hacking away at it before eventually we will be surprised. So that was the other thing for the single sources. So I just want to finish up now talking about what we can do with the LBI for pulsar timing arrays. So the first thing is just basically, improving each of the individual sources. So, getting rid of covariances of mostly DM variations with distance or anything like that. But the more interesting things here are then ways you can combine the results from multiple sources. The first one is improving the solar system ephemeris, and the second one is making some really ultra precise distance measurements to do coherent nanohertz gravitational wave interferometry. And so I'll cover each of those in turn. So at a fundamental level, pulsar timing makes its measurements in a dynamical frame, and that dynamical frame is referenced to the solar system barycenter. When we measure pulse times of arrival, we're making them on a moving platform, which is the Earth, and more specifically an observatory on the Earth that's moving around, and all things going around the sun, or around the barycenter, I should say. And so we need to take those measured times of arrival and put them in a place where they're not moving with time, which is the solar system barycenter. But so any errors in the solar system ephemeris will lead to an error in the barycentric correction, and that will lead to a direction-dependent time of arrival error and time-dependent as well, which is pretty deadly for searches for nanohertz gravitational waves. So one thing we can do, like people have been improving the solar system ephemeris for decades, well, as long as people knew there was a solar system, really. And we do that by observing spacecraft that are doing flybys of other planets, and lunar laser ranging and all kinds of other techniques put together. But one thing that another way we can do this, like more directly for this use case of interest of like pulsar timing, is to use VLBI positions, because VLBI measures positions in a quasi-inertial reference frame, which is defined by an ensemble of very, very distant quasars, often in the distant universe. And if these frames are not well tied together, then the positions of pulsars that are measured by timing in the barycentric frame will differ from the positions that we measure for pulsars in this inertial frame using VLBI. So this was just an illustration of what I exactly just said, so it's a bit superfluous. But if we don't know the solar system ephemeris properly, then this view that we have here can tilt around a little bit or move a little bit, and that's going to mean that positions that we measure for pulsars with timing will not agree with positions that we measure with the LBI. So that sounds simple. All we have to do is get a bunch of precisely measured positions, and from pulsar timing of good millisecond pulsars, you can get sub-milliarc second positions quite easily, and the relative precision that we can get for positions using VLBI can also be sub-milliarc second very, very easily. I mean, I showed the uncertainty on some of the parallaxes before is at the level of kind of 10 to 15 microarc seconds. So way beyond that. But to do this comparison, it's not just the relative position of a pulsar that's important, but it's absolute position on the sky. And what that means is, I said before that the VLBI positions are measured in this inertial reference frame. That's ultimately defined by an ensemble of several thousand radio quasars, but usually the calibrator source that we're using for a given observation is not one of those 2,000 odd sources directly. It's some other source whose position is not known quite so well. So that in this little plot I'm showing down here, this might be the pulsar called out in yellow and the calibrator called out in blue. But so we have some assumed position for the calibrator, and relative to that, we measure the offset to the pulsar very, very precisely to that kinds of tens of microarc second level. But if our assumed position of the calibrator was wrong by a few milliarc seconds, then because the first thing we did really when we were deriving those propagation delay errors through the ionosphere and everything was to say this source, this calibrator source should be, right at this position where I said it should be, right here. If its true position is over here, we've dragged it down like this. And what's going to happen is the pulsar is also going to be dragged away from its true position. So our imperfect knowledge of where our calibrator source is will be transferred to the target. So to get this right then, all we need to do, very easy, is just get the positions of our reference sources very, very precisely. And I'm being facetious because it's not quite that simple. The set of several thousand defining radio quasars, that their positions are defined at higher frequency, and we tend to observe at lower frequency, as I mentioned before. So we need to take into account all kinds of messy effects in the sources that produce the radio emission in the first place. So big blobs of material being ejected from jets that are being powered by accretion onto supermassive black holes, and it's all a little bit tricky. So getting down to the kind of like couple of milliarc second level is really easy, and then getting that last order of magnitude to the kind of sub-milliarc second level is quite a bit harder and requires multi-frequency, multi-epoch observations dedicated just to locking in what's the right position of your calibrator source. So this is an ongoing work. The paper that I talked about before from Howe that was just published this year generated 18 new positions, which is an absolute bonanza. And there was a handful of earlier ones as well. So there's about 20 usable sources now, but none of them have really, really high precision absolute positions yet. We were really focusing on the relative stuff to get the proper motion and the parallaxes. And so this is just a call out of one of the table from Howe's paper, where you can see this is the first thing shown here is the nominal precision. That's the kind of the precision in the offset from the calibrator. And so you can see they're all at the kind of 10th of a milliarc second level, super, super precise. And then there's 3 different systematic contributions following that are all at the level of maybe a milliarc second or so. So we have the data in hand to knock them all down to the sort of sub-milliarc second level. And that's what Howe's sort of working on as part of his first postdoc. And so the last thing, I seem to have done well in using more time than I said I would, but this is the last thing I wanted to talk about, was ultra precise distances for nanohertz PTA gravitational wave detection. So when we're talking about detecting a gravitational wave background, I'm sure this would have been covered earlier in the workshop already. The stochastic background, the easiest way to detect it is to go and look for an angular correlation on the sky, the Hellings and down curve, where effectively we're looking at the correlated motion of the Earth induced by gravitational waves passing by, whilst ignoring the effect of the gravitational wave background on each of the pulsars, because we can't know it, right? We're sitting floating on a sea, and they're sitting floating on a different part of the sea, and we can't know what's going on there in a stochastic background sense. So we're only sensitive to half of the effect, really, the effect on the Earth, but not the effect on the source. However, were we to consider a single supermassive black hole binary, and this is, I don't know why this one would be within our galaxy, apparently, at a comparable distance to the pulsars, but it's an artist's impression. Then we can calculate, if we have a source of known position, of known frequency derivative, if it's an evolving source, and we know where we are and where the pulsars are, we can calculate actually not just what the effect is of that gravitational wave passing the Earth, but also what the effect is of the gravitational wave passing by each of the 2 pulsars in our pair that we're cross-correlating. And so that would mean that rather than neglecting the effect of the gravitational wave on the pulsar and just treating that as an additional source of noise, we could, calculate it and use it. And the sensitivity to this, to detecting this single source of gravitational wave emission will go up quite substantially. However, that only works if you know the distance to the pulsar to within a small fraction, let's say, of the gravitational wave wavelength. So if you're looking at a gravitational wave period of, say, 10 years, that would mean you'd want to know the pulsar distance to maybe a light year or a couple of light years at most. So let's say less than a parsec, because that's a convenient thing to use. So at the moment, there's only one millisecond pulsar that's a part of a pulsar timing array out there with a sub-parsec distance uncertainty, and that's the closest and brightest MSP, JO437. But there are a couple of others, and the distance uncertainty there is less than a light year already, actually. It's a fantastic source. However, there are several others that are within reach. There's 2222, where the uncertainty is of order a parsec, and I'm sure we could knock that down by a factor of several without trying too hard. And 0030 plus 0451, that's, it's at the 5 parsec level and would probably require a pretty concerted effort, but I think we could get there. Plus, there's a couple more that haven't really had a serious effort in the past because they're a bit fainter or they're a bit further south. But even just getting to 3 sources where the distances were known at sort of sub-parsec precision, so you could do a coherent search for kind of decade period gravitational wave sources, would be a really significant boost to the sensitivity for those searches. So I think it's worth investing in the future. And as was the question before, like can we get to maybe order of magnitude level improvements in our parallax position? I think we can with a lot of effort, and if we can, then we can open up a significant number of sources that we could potentially get distances at this level. So that's it. I just wanted to wrap up with a slide looking to the future. The current best practice, as I said, gets us to kinds of tens of microarc seconds of parallax uncertainty. So for a source at a kiloparsec, that's great. You can get a distance to a few percent. For very nearby sources at several hundred parsecs, you can get to that kind of 1 parsec level uncertainty, just about. But I think we can do a factor of few better, and that mostly comes from adding new and sensitive and wide field facilities such that we can access multiple fainter calibrated sources at once and do this more complicated but better calibration that I've been banging on about. So that's already pretty significant in terms of like the volume or the number of pulsars which are then feasible, probably a factor of 10 more volume. But I think the thing that I'm more excited about is going after that handful of really high profile sources, whether that's the double pulsar or some newly discovered highly relativistic double neutron star system, or the most extreme binding energy ratio tight white pulsar white dwarf binary for doing dipolar gravitational wave tests or whatever. The ones where you've got a great observational measurement and you need a really good distance and transverse velocity to subtract off these kinematic effects and make the highest precision GR test that you can, and also the stuff with the ensemble searches with PTAs as well. The last thing is improving the absolute astrometry of a significant sample of well-timed pulsars so that we can do these precision solar system ephemeris tests. So that's all I had. I think that's very close to 50 minutes through more good luck than good management. So I'll say thank you and take questions.
Great. Thank you, Adam. Can you hear us?
Yeah.
Okay, great. So we have time for, 10 minutes of questions or so. We have a couple questions in the audience, and then I can't see the Zoom chat, but if folks on Zoom have any questions, please just put a little message there and we'll come to you after a couple audience questions.
Hi, very nice talk. So my question is, of course, I don't work in this field, so maybe you have already covered it, but I'll just shoot it anyway. So when you going back to the point where you are trying to localize a source very accurately, so basically you need a neighboring source which is close, and then you are looking at that, assuming that what is happening to the nearby source is exactly what is happening to the pulsar, and then you are trying to correct for it. Now when it comes to VLBI, the antennas are sort of thousands of kilometers away, right? So is there an assumption that the ionospheric effects are the same to all the detectors? And also, what is the time scale in which the detectors, the ionosphere changes? Because if you're by the time the SNR builds up for the nearby source, the ionosphere might have changed, right?
Yep. Those are all great questions. The first one is that there's no assumption that the ionosphere is common over all of the antennas, because otherwise it would cancel out. Anything that's common actually doesn't matter. So if you had a slab of ionosphere and it introduced a 10 nanosecond propagation delay, but it was the same 10 nanoseconds for every antenna, then we wouldn't notice it. But so what all of these illustrations are basically what's happening to the signal for it on its way to a single antenna here. And so what we then measure ultimately is the difference in the difference, if that makes sense. So we're measuring like the measurements we make are between pairs of antennas. And so you have a difference in a propagation delay on this pair of antennas looking at the direction in the calibrator, and then a difference when looking towards the target. And then you have many such pairs of antennas that you can work with. So I feel like I haven't explained this very well, but yeah, you can basically think of it as every antenna is getting its own solution for the ionosphere. It's basically what's the propagation delay along the path length above this antenna. And what was the other question? Oh, the timescale. Yeah, indeed. So there is that trade-off, and this is something that's in place for any kind of radio interferometry imaging, that you need to make the solutions within a coherence time, basically. And the coherence time is very, very long at centimeter wavelengths. But we're not interested in just staying coherent. We want to also basically have effectively no residual systematic errors at all. So a lot of the most problematic disturbances have a timescale of around about maybe 10, 20, 30 minutes. And these are these traveling ionospheric disturbances that kind of ripple around the ionosphere. So that really sets, your timescale of saying, I'd like to make solutions on timescales of 2 or 3 minutes, typically. If you're lacking in signal to noise, you just have to suck it up and make it on 5 or 8 minute solution intervals. But if you've got lots of signal to noise, you might choose to do it on 30-second solution intervals. But yeah, of order a minute or 2 is probably the rule of thumb, and that's what sets the minimum brightness of the source that you can use, because if you go too faint, you can't get a solution in that time.
Okay, great. So coming back to the first part, so I understand that it is like a matrix equation, that you have an array of like antennas or antenna pairs, and then you have some sources, and then you are kind of like trying to, you are solving pairwise, which kind of means like there is a linear matrix operator which you are sort of getting. Is that a correct understanding?
So there are different ways of doing that solution. What's often commonly done, so when doing the initial solution, it's quite common to take a single antenna as the reference, and you try and look at each baseline from every other antenna to that one antenna, and use that as a starting guess, and then do a gradient descent optimization, including all of the other baselines after that. But there are other ways as well. But I think, honestly, that's one area of the calibration I've never worried too much about, and I've always trusted the software packages to do it properly for me. And what I am worried about is the interpolation between solutions once they've been obtained.
Okay, so I mean, the reason I was asking is that where I was trying to go to is that, can you in this process completely get rid of the calibrator part, and you can solve for the source location directly using all the arrays together? I mean, instead of invoking any of these, the nearby source and so on. I mean, is it even possible theoretically, or you always need to have a reference source?
No, so I mean, if you don't, it's possible to try and estimate source positions without using any calibrator information. But essentially, then you can think of it like this, I guess. Every pair of antennas, every baseline that gives you one measurement, that gives you an estimate of a position at that snapshot in time. But if there are calibration errors, that position will get moved a little bit. So if we take now many pairs of antennas and many times, if there are no errors, no calibration errors, all of those points, if you were to kind of like add them up on the sky, will all land in the same place and you'll get a nice, beautiful image at the correct location. If there are some errors which are persistent in time and not changing, then you might still get a nice looking source, but it's at the wrong spot. So, and that's what would happen then if you tried to make an image without doing any calibration, the source would be in the wrong place. But more commonly, there's actually, those errors will be varying in time. And so what you'll get is actually not a nice image of the sky that's at the right position or at a wrong position, but actually something that's all smeared out and messed up. And that's the effect of the calibration errors. So you can't, you can do that if you basically make an image of the sky without applying any calibration, but it'll look like a big mess. And you could try and infer the position and the calibration errors from that directly, but there's a circular reasoning going on there. There's no unique solution, basically.
Cool. Thanks, Adam. I think we have a couple other questions. I'll go to Avinash first and then Gopu.
Hi, I have a question regarding the choosing the reference point using the quasars. So for this case, do we need to observe it at regular intervals?
Yeah, so the defining sources of the International Celestial Reference Frame, they are observed regularly, and all of those things get thrown into some massive fit that comes up with all of the positions of all of the sources and a bunch of other nuisance terms, and then the 3 coordinate dimensions that we care about. When you, if some of those sources, you would see, if you look at those images as a function of time, you'll see them change. Like there'll be it'll start off looking point-like, and then they'll grow a little extension, and maybe a blob will come off. So that's a transient ejection of material coming down this jet. And unless you take that into account when deriving, maybe I'll take one more step back. When we do calibration, we force our data to look like a model. And so if the model that we give to the calibration process is not actually a good representation of the actual sky brightness distribution, then the calibration process will do its best to make the data look like the model. And in doing so, will introduce some systematic shifts by trying to make, for instance, imagine the actual source looks like a core and a jet, like a blob with some other blobs coming out, but our model was simply a point source. It says, that all the emission should be coming from one place. What will effectively happen in the calibration solution, it'll sort of shift this image that actually has some spatial extent. It's not completely just a point, such that the centroid of the emission is kind of at the position of that point source that we gave as a model, if that makes sense. So, and that's not right. And so that would then shift any images of any other sources that we made when applying those calibration solutions. So you would naively then say, so we should be making a model of our calibrator source at every single epoch, and using that as the model to derive the calibrator solutions, and that will take away any time dependence of the calibrator. But unfortunately, the number of degrees of freedom is the same as the number of things you're solving for then, and you're actually, it's not possible to ensure that you've got both the right model and the right calibration solutions, if that makes sense. So generally speaking, the assumption that we have to make is that the calibrator sources are constant over the duration of our observing campaign. And that's one of the reasons why we tend to do our observations over a period of maybe a year and a half. So enough to sample, 1.5 or 2 parallax sine waves from the Earth's motion around the sun, rather than doing really, really long ones, because if we observe over 10 or 15 years, there's more chance that the calibrator sources will evolve and our model, which we've kept constant, won't be a good model. So the other thing that we can do to try and get around this is, before we start, go and look at the calibrator sources that we might choose to use and see if there's any historical data, and if any of them look like they vary a lot. So blazars are terrible sources for this, like things where you're looking very close to the down the axis of the jet that's being produced by the supermassive black hole, then you're probably better off not using that as a calibrator source and picking another one, even if it's a bit fainter or a bit further away, but likely to be more stable in time. Did that answer the question, or did that just lead to massive amounts of confusion?
Thank you very much. And I have another question. So this is about connecting celestial reference frame using quasars to the, to the barycenter kind of frame. But then you have to worry about solar motion constant, which I think some of them are, from the galactic dynamics textbook, we learned that, some components are not well determined. So will that introduce errors?
I have to say, this is not really my area of expertise. Like, I focus on getting the data points, and I'm hoping that someone else is going to turn them into the actual numbers and uncertainties on numbers. But I think that the situation has improved significantly with the advent of Gaia, right? Like that those solar motions are now known quite a bit more precisely than they were previously. So I don't think that's a dominant source of uncertainty anymore, but don't take that as gospel.
Okay, thank you. I have a follow-up question, just one more. So this is about, I've been hearing from Tai-Hoon Jung and others about their, this multi-frequency receivers, they're that to do for the KVN style observation where they have the SOP implemented for the FPT kind of thing. So that's usually for higher frequencies. Is that possible to do that for the low frequency, so that of course you worry about ionosphere, so if that can be taken care? Is there a possibility to do at the low frequency?
Yes. So I think that the reason for doing the frequency, what's it called? Yeah, the applying calibration across different frequency ranges at high frequency is mostly driven by signal to noise. So there's not very, the receiver temperatures get higher at high frequency and the sources get fainter. So you're getting hit from two directions at once. And so it's just really hard to find good calibration good calibrator sources at very high frequency, and there's more of them at lower frequency. And so that's the motivation for using the lower frequencies to calibrate the higher frequencies. We don't have that problem as much at centimeter wavelengths because the coherence times are quite long and the number of bright sources is quite high, and the the system temperature of the receivers is reasonably flat. I guess the background's starting to raise a bit as you go to very low frequency just because of the synchrotron background. But, we're in a bit of a less hostile regime, I guess. So I don't think there's so much advantage necessarily in trying to do transferring of calibration from one frequency to another. That said, where there is potentially a very advantageous way of using wide frequency bandwidths is to actually fit for the ionospheric calibration directly at the direction of the target. And this was actually already first done 20 years ago by Walter Briskin, because any ionospheric delays actually have a dependence on wavelength. And so we don't have to just let them bleed straight into the geometric terms. If we can observe over a wide bandwidth and see the change in apparent delay as a function of frequency, we can say, well, the source isn't moving on the sky as a function of frequency. I know that for sure. So that must just be the ionosphere. And if I can fit that and take it out, then it's gone. And it's gone actually right in the direction of the source. The disadvantage, of course, is you need the source to be bright enough that you can do that solution over a relatively wide frequency range. But again, with the advent of more sensitive facilities in the future, that may well become possible for a reasonable fraction of sources. And I would just mention as well that this is exactly the calibration approach that Chime is using for localizing fast radio bursts, because they have a very small number of outrigger telescopes. They have a nice sensitive detector and then a small number of outrigger telescopes, which is not dissimilar to other VLBI arrays where you have maybe one big dish and some smaller ones. And they're actually aiming to not do traditional phase referencing at all, but only take away the ionospheric calibration term purely by its quadratic dependence on wavelength. And so we could, if that works well, we can take some lessons from that and apply them here.
Great. Thanks, Adam. We have, I think, one more question, if it's okay. I know we're a little over,
Yeah.
but our next till 10:30. So Prabhu.
Yeah, thanks, Adam. This is Prabhu here, and this is related to the SK you were referring to. And have you looked at the SK VLBI beam and the backends, and whether how particularly if they are what is being thought about there is what you would recommend for SKA, particularly for a pulsar related geometry?
Yeah. So, for my sins, I was involved with writing some of the original use cases for the SKA pulsar timing, pulsar VLBI backend as applied to pulsar VLBI. So, if it wasn't good enough, I've only got myself to blame. We originally proposed for 4 beams because that seemed like what was the most that we could possibly ask for without the SKA having conniptions. Because at that time, every beam of the every phased array beam from the SKA was going to be running on its own hardware. And so adding an extra beam added an extra, this much cost. As more recently, the design of the SKA correlated beamformer has changed and has opened up the possibility of reusing some of the hardware that would be otherwise used for making other kinds of phased array beams, like, for instance, pulsar timing beams, if they're not being used for pulsar timing at that stage. So it's quite possible, like this is still, I think, the subject of an engineering change request, that there could be up to 16 beams available for VLBI, which would be just fantastic. You could never ask for, I think you would struggle to use more than that effectively. However, you still need the capability to record all of those beams and send them off to a VLBI correlator to be processed. And I think that's actually likely to be the bigger logistical challenge initially. Like if you want to be recording n times 4 gigabits per second, and n is a rather large number, like 8 or 16 or something, it's actually really a lot of data you're trying to capture and then ship out.
Cool. Thank you, Adam. I think we should end here. I'll just make a plea that I think it's really, really important that we time these do VLBI on these few best PTA pulsars. And we're not far off from single source detections. And I think getting distances to within a wavelength, like you say, for 3 or 4 of them is super valuable. I think we need to get on that. That was a great.
Oh, thank you. Yeah. Well, so keep in touch if you want to talk about any joint proposals.
For sure. Yeah. Okay, cool. Thanks so much.
Okay. Thanks, everyone.
Yeah.
Pause.
Thanks, Adam. Bye-bye.
Bye.
Okay. So do we have a small break now before the 10:30 talk? Okay. So we have 21 minutes before our next talk. What's that?
Manjari, can I just slip in a word? So, so we have a 3P plus committee meeting at 1:30 today, and I don't know whether Maura is attending that or not. So, are we likely to finish before that?
Okay, and there is another point. We are actually postponing that Indo-US meeting on Sunday because Gopu has another meeting, TIFR meeting.
And again, we have to go for the 1:30.
No, that's fine. That is fine. That is fine. I was just asking that, will we be free at 1:30 Indian Standard Time?
Yes. We have only one more talk today from 10:30 to 11:30. We don't have anything. Okay. Sanjit's talk at 4 to 5 because we need to cancel that Indo-US thing.
Okay, great. Okay, thanks.
See you at 10:30 again, and then at 4.
Yeah, sure.
And tomorrow, I think you guys got it.
Yeah, so we will join at 1:30, the steering committee thing. Yeah, okay, great.
Now I have to find the next speaker.
Can lunch? I thought you did lunch at 2:30. Is that okay? There's still lunch.
Lunch.
So when is the 3 to plus before that 4:30? I think any, you will finish the lunch. We will be fast and go. I'll join from my house.